In this video, we want to look into the results of the two simulations that we made in the previous video. One was our original delta development model, and the other one was the same model but adding a cohesive sediment fraction to the system. Now both models are finished. I'm gonna minimize this presentation and open my quick plot. Now I have the quick plot and I'm going to open the two trim files that I have. The first one from delta 01 and the second one I will open from delta 2. The first thing that I want to look at is generally how the final results of these two are different. One of the things that is nice to do when we have a large morphological factor is to change also our time in the quick plot to morphological time. Now we also know when in the morphological time we are. I choose the bed level in water level point, and just for the fun of it, I also change this to the continuous shade and use automatic color bars. This is delta 2, so the one with additional mud. You can see how this looks like. That's the outcome after about 1,000 days of simulations. And if I choose delta 1, look here, it's delta 1, for the same time, I see a different outcome. So you can see that here it's a visible difference between these two simulations. In the left one, we have cohesive sediment in the model. In the right one, we don't have. You can see that in general, the development of the delta is a bit slower when we have fine sediment and cohesive sediment comparing to the sand, but you can also see that the extent of the changes, so extent of the influence of the river that bringing cohesive fine sediment is further. If you follow this contour line, you can see that in this simulation with fraction of mud it has changed, but here we can see that it's more or less straight. So you can see that when we have mud, because they can be suspended in the water for a longer time, and we have also advection diffusion sediment transport with mud and cohesive sediment, they can be suspended and move in the water for a longer distance and drop further in our system. Okay, I will keep this left one, which was our second model, open, and I close this. But we can see quite more outputs and look at different things here. For example, the next thing that I want to look into is a cross-section at this part of the model. So let's look at delta 2, and then I will look at the cross-section at this location. For example, somewhere here. It's about 82 at the cross-section number 82. Then I change also this to xval, and then I say quick view. And now you can see that this is a sort of a cross-section of the river and the shallow areas that has been developed at the end of this simulation at this specific cross-section. You can see that there are some channels and there are some flat areas above sea level. But now, if I want to see what is the property of the material that have built these shoals, and what is the property of the materials which are down under this canal, I can go and look into the sediment volume fractions. If I choose this, I can see that I have two of these here, two of the sediment fractions that I use in the model. I use sediment mud here. And then I say, okay, in all the layers inside the bed, I want to see that. And I change the color limits, manual 0 to 1, because I want to see them in percentages. So between 0 to 1, it's nice. If I look at the same cross-section now in time step number 1 or 2, 2 is better because something has happened. You can see that all around the model, all in the cross section inside the bed. So you can see that from the depth of about minus 2.8 for 5-meter sediment that we had, it is about 20% of mud. That is what we put in the model. So it's the beginning of the model. But if now I move to end of the model, 241, and I say quick view, you can see that bed level has changed quite a bit. So this is a canal and the shoals that we saw before. This is a channel, this is a shoal. And you can see that also the percentage of mud sediment is very different now. So you can see that in these shoals, we have much more mud sediment, so even sometimes up to 100% of mud covering the top of these areas. But if we look at inside the canals, we see that the mud is very little there. So it goes even sometimes to 0%. So sometimes the bottom of the canals is 100% sandy, which is also expected, similar to reality. But also you can see something very, very interesting here. You can see that there is a very dark blue here, which indicate the sandy ridge in the place which we don't have the canal at the moment. So it gives us the impression that maybe during the evolvement or evolution of this delta, there used to be a canal here which has moved towards the right later. Let's try to see if we can find that in the simulation. So I will put this here as well. And then I will say, okay, let's look at that time step of 200 and the same cross section and everything similar. And we click on quick view. You can see that, yes, about half a year before, so this is July 2023 and this is January 2024, about half a year before, actually there it was part of the canal. So we had a channel here, we had a canal here, that bottom of the canal was very much sandy. But the canal had started migrating towards the right, and you can see that the new canal is here. Yeah. So I also put this here to see this diff changes. This we don't need. This I will minimize and keep for later. And then I go back to my quick plot and say, okay, I also want to look at the time a bit before that, like 150. And we can see that here we can identify the initiation of this canal. So the canal was initiated here, starting digging into the mud, into the layers, transporting the mud outside the canal, and the bottom of the canal was pretty much sandy. You can see here it's getting sandier and sandier because the percentage of the mud that we are looking at is 0, and then the canal has migrated towards the right, and it has left a sandy area inside the bed of the new delta. So it's very interesting to see. Even also in the reality, you can find these type of sand ridges in the deltas, which has been the sign of previous rivers or previous channels. So this is one of the things that we could look at. Now I'm gonna close this tree and try to look at some other interesting things that we can see. Now I'm going to look into a sort of a 2D on the map of the model, and I'm looking at the top of the bed, the first layer of the bed, on the top of the bed. And again, I'm looking at the sediment mud first, and then I look at the sediment sand as well, which is of course the inverse of the sediment mud. But you can see that this is mud, this is sand. You can see that if you look at how the canals have been developed here, how the channels have been developed here, inside the channel there's almost no mud and there is fully sand. However, further in the sea, when we go to these locations, we can see that mud is prevailing. So on top of the bed there's more muddy than sandy in these areas. Maybe it's also nice to go and look at the cross section here at this location. So I'm going to close these two. I open this I choose a cross section in a deeper area of the model, for example, somewhere here. And now I look at all the layers under the bed, and I look at the final time step there. So let's look at the final time step. You can see that in this place we have some deposition there, but you can see that deposition is mainly mud. Why we can see that? Because we have chosen sediment sand here, and the percentage of the sediment sand in the top layer is almost zero. So the mud that was coming out of the river has traveled almost till these locations and are dropped on the top of the bed and has made this hump and almost fully with mud. So this is how you can look into the result of these type of models. You can make other cross sections for yourself if you like, and look how this has been developed. I can also show you one more output, which may be interesting for some of you, is the sediment concentration. So let's look at the sediment concentration. This we can choose it here. Sediment mud gives us the sediment concentration for the cohesive sediment. And if I choose time number 2, again at the beginning of the model, I will change this also to automatic, and I will look at all the surface. Yeah. So, and then say quick view, we can see that at this time, which is practically early in the model, so morphological time of 0 almost, this from the river, zero point 0.2 kilogram per cubic meter of mud or cohesive sediment is coming to our model. This is exactly what we put at the boundary condition. So it is interesting to see it also in the results to make sure our model is correct. But you can see also as soon as this enters the model, because it's finer sediment and it can travel longer in the water, it has started coming into the model very quickly. If I look at the same thing, but for sediment sand, which gives me the concentration at very early times of simulation for sand material, then I see that it is, although very similar values, but it is very, very close to the boundary of the river, so very close to the river mouth, because the concentration of the sand could not extend in the water because sand is heavier and it is more transported as a bed load that can stay suspended much less than mud in the water. So you can see also the differences of this. And now if I move this time step to further, you can see that the mud is changing and moving inside the model quite a bit compared to the sand, that the concentration of the sand is pretty much only very close to the boundary and in the main canals that it is developed in the delta. Okay, so this was also some other interesting outputs that we could see and from this model and see the effect of mud and cohesive sediment in the delta development.